The vastness of space is both alluring and daunting. We look to the stars and dream of reaching distant worlds, but the distances are immense, measured in light years. Science fiction, like Star Wars, has long toyed with faster-than-light travel. One concept that captivates is the warp drive. While theoretical, it offers hope of traversing the cosmos at unimaginable speeds. Imagine voyages to other star systems within human lifetimes. Warp drive ignites our imagination, offering a future where space is no longer an obstacle. To understand warp drive, we must first delve into the mind of Albert Einstein. His theory of general relativity, published in 1915, revolutionized our understanding of gravity. Einstein proposed that gravity is not a force that acts over a distance, as Newton believed. Instead, gravity is a consequence of the curvature of space-time. Imagine space-time as a fabric. Massive objects like stars and planets create dents in this fabric, causing it to curve. This curvature is what we experience as gravity. One of the most profound implications of Einstein's theory is that it allows for the possibility of space-time itself being warped and manipulated. Imagine stretching the fabric of space-time in front of you while simultaneously compressing it behind you. This, in essence, is the basic idea behind warp drive. By creating a warp bubble around a spacecraft, we could theoretically distort space-time in a way that propels the ship forward at incredible speeds, potentially even faster than the speed of light. This concept, while mind-boggling, emerges directly from the equations of general relativity, suggesting that the possibility of warp drive is not merely a product of science fiction, but rather a potential consequence of the very laws that govern the universe. The key to warp drive lies in manipulating space-time itself. Instead of traveling through space in the conventional sense, a warp drive would create a bubble of distorted space-time around the spacecraft. This bubble would contract space-time in front of the ship and expand it behind, effectively creating a localized wave on which the ship rides. The spacecraft itself would remain stationary within the warp bubble, protected from the extreme forces involved in distorting space-time. Imagine a surfer riding a wave. The surfer doesn't propel themselves through the water so much as they are carried along by the wave's energy. Similarly, a warp-driven spacecraft would be propelled through space-time by the distortion of the warp bubble itself. This method of travel elegantly circumvents the limitations imposed by Einstein's theory of special relativity, which states that nothing can travel faster than light through space-time. By warping space-time itself, the spacecraft isn't technically exceeding the speed of light locally. Instead, it's taking a shortcut through the cosmos, utilizing a warped region of space-time where the normal rules of distance and speed are altered. Creating a warp bubble, however, is no easy feat. It requires a form of energy with a peculiar property: negative energy density. In simple terms, negative energy is a concept in physics that describes a state of energy lower than the energy of empty space, also known as the vacuum state. While this might sound like something out of science fiction, there is some evidence to suggest that negative energy might actually exist. For example, the Casimir effect, a phenomenon observed in quantum physics, suggests the existence of negative energy densities in certain configurations. However, harnessing enough negative energy to create a warp bubble remains a significant hurdle. The amount of negative energy required is thought to be astronomically large, far beyond our current technological capabilities. Furthermore, the very nature of negative energy is still not fully understood. Whether it can be created and manipulated on the scales necessary for warp drive is a question that continues to puzzle physicists. Despite these challenges, the pursuit of understanding and harnessing negative energy represents a crucial step towards making warp drive a reality. Section 5. Hyperspace versus warp drive. Separating science fiction from scientific possibility. The concept of warp drive is often compared to hyperspace travel, a staple of science fiction universes like Star Wars. While both allow for faster-than-light travel, they are fundamentally different. Hyperspace, as depicted in Star Wars, typically involves entering an alternate dimension where the normal laws of physics don't apply. This alternate dimension is often portrayed as a swirling vortex of colors or a tunnel of light, allowing ships to traverse vast distances in a short amount of time. Warp drive, on the other hand, operates within the known laws of physics, specifically Einstein's theory of general relativity. It doesn't rely on entering another dimension, but rather on manipulating the fabric of space-time itself. While hyperspace travel remains purely in the realm of science fiction, warp drive, though highly theoretical, has a basis in real scientific principles. This distinction is crucial, as it elevates warp drive from a mere fantasy to a tantalizing possibility, albeit one with significant challenges to overcome. Section 6. Navigating the unknown, practical challenges and safety concerns of warp travel. Even if we could overcome the hurdle of creating negative energy and generating a warp bubble, numerous practical and safety concerns must be addressed. One major concern is the potential for time dilation. According to Einstein's theory of special relativity, time passes differently for objects moving at different speeds. At speeds approaching that of light, time slows down for the moving object relative to a stationary observer. This means that a journey at warp speed, while seemingly short for the travelers, could result in a significant time lapse back on Earth. Another concern is the potential for collisions. A warp-driven spacecraft traveling at such incredible speeds would need to navigate through space with extreme precision. Even a tiny object like a grain of dust could cause catastrophic damage if it collided with the ship at warp speed. Furthermore, the very act of creating and collapsing a warp bubble could have unintended consequences on the regions of space-time it interacts with. Understanding and mitigating these risks is paramount before we can even contemplate embarking on a warp-driven journey. Section 7. A warp perspective. Imagining the journey at faster-than-light speeds. Imagine yourself aboard a spacecraft equipped with a functional warp drive. Unlike the swirling colors and streaks of light often depicted in science fiction, the actual experience of warp travel might be surprisingly mundane from the passenger's perspective. This is because the ship itself is stationary within the warp bubble, and it's the space-time around the ship that is being manipulated. As the warp drive engages, there might be a subtle distortion of the starlight visible outside the ship, as if the constellations themselves were being stretched and compressed. However, the most profound realization might be the lack of any sensation of movement. There would be no inertial forces, no G-forces pushing you back in your seat as the ship accelerates. It would be as if you were standing still, even as you traverse light years of distance in what, from your perspective, feels like an instant. This disconnect between the immense speeds involved and the seemingly static nature of the journey within a warp bubble would likely be one of the most peculiar and awe-inspiring aspects of warp travel. Section 8. Charting the course, expert opinions, and the future of warp drive research. While warp drive remains highly speculative, it has captured the imagination of physicists and continues to be a subject of serious scientific inquiry. Some researchers, like Dr. Miguel Alcubierre, who first proposed a mathematically sound model for a warp drive in 1994, believe that continued research into advanced propulsion systems is essential for the future of space exploration. Others, like the late Stephen Hawking, have expressed skepticism, citing the immense energy requirements and the potential for unforeseen consequences. Despite the challenges, research into warp drive and other theoretical propulsion systems continues. Scientists are exploring various avenues, including exotic matter with negative mass and manipulating the properties of space-time at the quantum level. While a functional warp drive may be centuries away, if not longer, the pursuit of this seemingly impossible technology deepens our understanding of the universe and pushes the boundaries of what we believe is possible. Section 9. Conclusion. A century of warp drive? The dream of warp drive, of traveling faster than light and reaching for the stars, is a powerful one. While we may be centuries away from even approaching the technological capabilities required to create a warp drive, the very pursuit of this dream inspires us to think beyond our current limitations. It fosters a spirit of exploration and discovery, pushing the boundaries of science and technology. Perhaps in the distant future, warp drive will transition from the realm of science fiction to scientific reality. Perhaps one day our descendants will look back at our time, not with pity for our limitations, but with admiration for our audacity to dream big, to imagine a universe where the stars themselves are within our reach. Perhaps, just perhaps, the journey towards warp drive will be as transformative as the destination itself, leading to unforeseen discoveries and innovations that redefine our place in the cosmos. The quest for warp drive is a